Hello everyone, my name is Elizabeth Reiser and I will be presenting on the synthesis of rhodamine B dimers, and my mentor is Dr. Pamela London. To begin with, I would like to discuss the two forms of rhodamine B that we have seen while working on our synthesis techniques. There's an open and closed form of this structure, and the pink structure on the left is the open and charged form of rhodamine B, and this is the form that is also colored, hence the pink for the structure, and this is a very pink dye. And this is shown in acidic conditions. And then when we have had more basic conditions, we have found that we get the spirolactone form of rhodamine B, which is the closed form of this structure. As seen right here, the hydroxyl group from the carboxylic acid over here creates a ring with the middle cyclic structure here. And this closed form we have noted to be not very colored like this structure here. Now to go into some more detail about the syntheses we have performed in this lab, we can see here that we have again the structure of rhodamine B, and this is just the open form showing here. And the carboxylic acid group is circled because this is the group where we add the amines to make amides of this rhodamine B structure. And up here is an example of a synthesis of one of the dimers we have created, this one being the rigid dimer. And we take two equivalents of our rhodamine B. We add it with a 1,4-diamine linker, and this is done in the solvent 1,2-dichloroethane. And then we use phosphorus oxychloride as a way to convert this carboxylic acid to an acid chloride. So then the acid chloride can react with our amine to create an amide and create these compounds that we desire seen here. And as I mentioned, this is the synthesis of our rigid dimer, which also has been called our trans dimer, which if you look down here on the range of flexibility of our dimers, it is second to be the most rigid of the dimers we have created. So this is a great example of what it looks like, where it is in terms of flexibility and rigidity, and what the general synthesis is for our reaction. And these pink circles shown are the rhodamine B structure to be represented as a pink structure due to the color of rhodamine B. And this change in rigidity versus flexibility can show some different characteristics via NMR and mass spectrometry that we have looked at with these various dimers we have created. To go into more detail now about the synthesis we performed to make these dimers, first the reaction is set up with a Schlenk line and a reflux condenser as seen in the leftmost picture. And the flask is flushed with nitrogen before adding solvent into the flask via a syringe. And the reason why this flask is flushed with nitrogen and run under nitrogen gas using the Schlenk line, it's a way to prevent water from being in this reaction so that we do not have to worry about hydrolysis of the acid chloride turning back into a carboxylic acid group. So once this has been flushed with nitrogen and we have our solvent added via a syringe, we also must make sure we have a reflux condenser attached to this reaction because it needs to run in a hot oil bath as seen in the photo for about 4.5 hours so that no solvent is lost. We use the reflux condenser. Then the product is washed with a strong acid and base seen in this middle image using an extraction funnel. This is done to ensure that the initial product we are obtaining from our reaction is rid of some initial impurities. We would then take this initial product and run an NMR to ensure that we have the product we are looking for. After doing so, we would run the product through a column runner instrument known as a biotage, which would give us a variety of samples in a lot of different test tubes as seen in this final photo. which we can then analyze using TLC plates and combine to then rotovap down and take NMRs of these more purified samples to see how pure our product is. Here we have a proton NMR sample of the synthesized aniline amide, and the primary reason that this NMR is important is it was one of the first compounds we created with using the synthesis method previously mentioned, and this was a way to confirm for us that that was a good synthetic methodology to use to create these different rhodamine B compounds. And this gives the characteristic aromatic peaks that we would hope for, as well as all the other peaks in this NMR. And one very important component of this NMR is around second 7.4, there is a narrow multiplet of peaks, and that is characteristic for the closed form of this compound, which I have right next to the NMR. And this indicates that what we synthesized was indeed the closed form of the aniline amide, and this is what the structure would look like. Another important NMR sample, again a proton NMR sample, is that of the cyclohexylamide. And this was again another compound that we made earlier on with validating the synthetic method that I've explained in this talk. And this NMR helped to reiterate that the synthesis worked and that we had created the projected compound. And similar to the last proton sample, the narrow multiplets around 7.4 again indicate that this is the closed form of the cyclohexylamide, which is shown right here to give an idea of what it looked like and what we likely synthesized in the lab based upon this NMR result. The last proton NMR that I want to share is that of the rigid dimer that I have talked about previously. This dimer is one that we had synthesized more recently, and from our previous compounds, this was helpful to know that the peaks that we were seeing in this NMR were what we would hope to see for the structure. And differently than the last two compounds in that kind of 7.4 region, the multiplets here are not as narrow and are more of a nice pretty pair of multiplets, which indicates to us that that is likely the open form of the rigid dimer, which can be shown here. And here's the whole rhodamine B with our diamine linker, and on the other side of this linker, because it is a dimer, there would be another rhodamine B structure, which could be abbreviated as RHB. And so from that peak around 7 for the multiplets, because they were not as narrow, that was indication for us that we had made the open form of the rigid dimer. To conclude this presentation, I wanted to hit on some future works that we could perform with rhodamine B dimers. The first would be using deuterated DCl as a way to go from the spirolactam form of these dimers to the more open lactam form that I've discussed throughout this presentation to see if we can go between the two as we please. The second would be to observe if methanol causes degradation of the rhodamine B dimers, because we noticed some odd things occurring while synthesizing and testing these dimers when they sat in methanol. And one way that we may test the methanol degradation of these dimers is by analyzing multiple proton NMRs of a sample over a period of time as it sits in methanol to see if there are any changes in the NMR data to that compound. Thank you very much for listening.